Hi everyone. Today I'm honored to introduce Roger Creel. Roger did his bachelor's at Amherst College and then his PhD at Columbia with Jackie Osterman. At that point, we were both graduate students and we ended up both visiting somebody else's lab of Rutgers at the same time, I think on accident. Got to know each other and followed Roger since then. He did a postdoc at Hui at Woods Hole, and now he's about to be our new neighbor at Texas A&M starting in August, so hopefully we'll get him back more. Today he's talking about sea level during the Holocene, what that means for Antarctica, but Roger has a ton of different interests, not just Antarctica, although that was my favorite topic, but also Greenland and glaciers, lots of thoughts about permafrost and sea level all over the place using GIA modeling, solar modeling. His interdisciplinary interests include ballet dancing, which is my favorite Roger fun fact. And a hot off the press announcement is that Roger has just won the Cozzarelli Prize from GNAS for best keyword. Wow. Excellent. Looking forward to it.
I'm going to turn my mic on and get going. Okay.
Testing. Okay, amazing. Thank you so much, Ruthie. I'm blushing. It's a real honor to be here. I look up to this department, and I think there's a ton of great science that goes on here. I've had awesome conversations with folks today. So, hoping when I think I'm allowed to say this because I'm not yet on faculty, because they're like the rivalry, but for now I can say I'm a huge fan, and I hope we can build relationships and collaborations between our two institutions. So I'm going to be talking to you today about the Antarctic Ice Sheet. The title of my talk is Retreat, Regrowth, and Rapid Thinning, Reconstructing the Holocene History of the Antarctic Ice Sheet. And the way this is going to go, I'll first talk to you about the motivation for this work. I'll then step through the tools that we're using to get at reconstructing sea level and ice sheet history. And then we'll talk about two projects. The first, how much and how fast did Antarctica grow and shrink in the Holocene? The second, how did Antarctica respond to abrupt Holocene climate events? Okay, so the motivation for this work is biggest picture that sea level is rising. Global mean sea level has been rising for the last century. It's currently rising by 3.5 millimeters a year. And in all of the rainbow scenarios shown up here from the Intergovernmental Panel on Climate Change, sea level will keep rising for at least the next 100 years. This will have impacts for coastal communities around the world. What makes sea level an interesting problem to dig into is that sea level is not rising everywhere the same amount. So here we're looking at present day rates of sea level along North America. I said 3 millimeters, that's the yellow arrow. So anywhere that you see the yellow arrow, sea level right now, local sea level is similar to the global average, but Gulf Coast sea level is rising faster, but there are places in Canada where sea level is falling by even more than it's rising elsewhere, local sea level. So as we start to try to understand the impacts that sea level rise or fall may have on communities, we need to start to disentangle the different processes that are causing local sea level to be different from global mean sea level. So for those of you who don't think about sea level on a daily timescale, I wanted to step through some of those processes to start to build a mental model for you of the sorts of different things that are changing sea level. So going from short to long time scales, on the shortest time scales, earthquakes can change sea level by locally by a meter in, let's say, a minute. A little bit longer, storm surges, changing sea level by local sea level by a meter per hour. Zoom out a little bit longer, and river discharge. Y'all have got some great rivers in Texas: Mississippi, Brazos, Trinity. Like a bunch of rivers are dumping fresh water into the Gulf. That water gets trapped along the coast. It increases sea level. So think a meter per day. Zoom out a little bit further, and resource extraction, water extraction, local processes like this, like permafrost thaw, subsidence can change local sea level by a meter per decade is a good ballpark. Zoom out a little bit further, and ice sheets are changing sea level by a meter per 100 years. Zoom out even further, a meter per 100,000 years, and we're thinking about mantle convection. So hot rock flowing in the solid state, lifting up parts of the world's crust, longer time scales. So we're going to be thinking about the Holocene, which is the last 12,000 years, and the last, say, 20,000 years. So we're really going to be focused in this talk on ice sheet processes. And as you know, we have two ice sheets. Currently, Greenland and Antarctica. I'm focusing mostly on Antarctica because for future projections, Antarctica is where we think a lot of the melt is going to come from fastest. Greenland, of course, also matters. Okay, so the motivating questions for us for the next 40 or 45 minutes are: one, when did the Antarctic ice sheet last melt faster than today? And two, how does Antarctica respond to abrupt climate forcing? Because we want to use the past as an analog for the future, and we want to understand how the Earth system responds when we hit it with a hammer. So to this first question, I'm going to marshal several scientific tools. We're going to use a combination of observations, geophysical models, and statistics. On the observational side, the question is, how do we learn about sea level? In the instrumental era, satellite altimetry over the last 40 or so years has given us a spatially continuous, detailed picture of sea level across the world's oceans. Tide gauges along a lot of the world's coastlines over the past century, in some places a little bit longer, have given us point estimates for sea level through time. But go back further than a century or so, and we have to use other means to get at sea level. So, for instance, salt marshes have a defined relationship to sea level now. That defined relationship allows us to go to ancient versions of them and say, let's radiocarbon date a sediment core from a marsh and reconstruct what sea level was over the past 5,000 or 6,000 years. Corals, coral microatolls, are another excellent sea level indicator. Raised beaches, they're in different coastal settings, there are different indicators, but all of these give us information about local relative sea level relative to the present at that location. On the geophysical modeling side, the question is, over the timescales that we think about, how do ice sheets growing and shrinking change sea level? So, ice sheets growing and shrinking first change gravity on Earth. This schematic and the idea behind it changed my life. I was going to be a carbonate sedimentologist before grad school, and then I read an interview with one of the founders of this field and thought, oh my gosh, I got to change my life. So I switched over to geophysics because I think this is just super cool. So a larger ice sheet has a larger gravitational field. It attracts water towards it. Ice sheets growing and shrinking also deform the solid Earth. So as an ice sheet grows, it squeezes mantle out from underneath it, squeezes rock out. That rock lifts up the solid Earth around the ice sheet in what we call a forebulge or peripheral bulge. As the ice sheet shrinks, that rock flows back underneath where the ice sheet had been. Because the Earth is viscous and has viscosity high enough to, much higher, let's say, than honey, this flow takes thousands of years. So Canada is still rebounding from the ice sheet that disappeared 6,000 years ago. Ice sheets growing and shrinking also change Earth's axis of rotation. So Earth is spinning, change where mass is on Earth, anywhere that's not exactly on the pole, and the rotational axis shifts. Water responds to that change in rotation basically instantaneously, but rock doesn't. So because of that water shifting but the rock not shifting, you get a checkerboard bihemispheric pattern of sea level just because of rotational axis shifts. So add together gravitation, deformation, and rotation, and you get what we call glacial isostatic adjustment modeling. And what's neat about glacial isostatic adjustment modeling, which is building a numerical model to predict how sea level will change, accounting for these different effects as ice sheets grow and shrink, assuming different viscoelastic structures for the solid Earth. What's neat about this is that each ice sheet has its own, what we call, fingerprint. So this is, what we're looking at here is the sea level fingerprint of West Antarctic ice sheet collapse. So this diagram answers the question, if you instantaneously remove enough ice from West Antarctica to increase global mean sea level by 1 meter, where does the water go? And in red, sea level's falling. So near Antarctica, you have less gravity, you have rebound, you have a rotational effect. Near Antarctica's relative sea level actually falls, whereas far away from Antarctica, sea level rises by more than the global average. So you could imagine, this is for Antarctica, but you could imagine for North American ice sheet, this pattern would be kind of flipped on its head. Same for Greenland, same for the Eurasian ice sheet. So each has a distinct fingerprint that we can use to tell stories about how these ice sheets are contributing to sea level through space and time. Okay, on the statistics side, the second part of this talk is going to have a little bit more complicated statistics, but for the first part of this talk, we're going very simple. We are simply comparing relative sea level data to glacial isostatic adjustment models. And so what I want to argue today is that because sea level changes everywhere when you melt an ice sheet, in order to get at this question, when did the Antarctic ice sheet last melt faster than today, we actually need to answer a related question, which is, how high did global mean sea level get in the Holocene, when what was sea level in different places, and use that to back out Antarctic ice volume? Okay, we also have to answer then a related question, which is how much ice was on land in the Holocene? And we've got 3 candidates. We've got Antarctic, Greenland, but also mountain glaciers are a contributor. I'm now going to review briefly what we know, kind of the state of the field about these different ice sheets to build your intuition about what global mean sea level might have been doing. So, on the Antarctic ice sheet front, there's growing evidence from a bunch of different sources suggesting that over the last 12,000 years, at some point, the Antarctic ice sheet was smaller than at pre-industrial. So this is coming from ice cores. This is coming from what we call nunatucks, these exposed mountains sticking out of the ice. This is coming from parts of Antarctica that are not glaciated, where we can see the coastline lifting out of the water as it's deglaciated. This is coming from marine sediment cores, both inside the grounding line of the ice sheet and out on the margins. So Antarctica, we think, was smaller at some point. Greenland ice sheet, similar story. This is a modeling study from a couple years ago. Time is moving from 12,000 years ago at left to 0 at right, and we're looking at cumulative mass change. So from the beginning of the Holocene to now, this study is placing, for most of these simulations, peak smallest Greenland at about 8,000, maybe for some of them closer to 4,000. The field evidence supports this. We think Greenland was smaller and then regrew. On the mountain glacier side, this figure is not my figure, super busy. But so time is now going from 12,000 years ago at top to 0 at bottom, and we're looking at Alaska, Arctic Canada, these different Arctic regions. Anywhere that's yellow, mountain glaciers are smaller than present or retreating, and blue is they're advancing. So if you kind of squint, early Holocene, mountain glaciers are retreating, late Holocene, they're advancing. So mountain glaciers from this picture would be smaller in the Holocene than at pre-industrial. And this kind of makes sense given what we think was happening to temperature at the poles during the Holocene. So this is from this is two differences between 12,000 years ago and 6,000, and then 6,000 to 0. The warm colors mean temperatures warmed up over the Holocene in this modeling result, particularly at the poles, and then they cooled down over the last 6,000 years. And I think it's important to note that there's a really actually delicious debate in the literature about what was global mean temperature in the Holocene. It's like a nature slugfest, just like people taking each other out. But for our purposes, this actually doesn't matter because what we care about is what the temperatures that the ice sheets are seeing. And at the poles, there's very little argument that at least in the northern hemisphere, mid-Holocene temperatures were higher than present. So add this together. If Holocene ice sheets and glaciers were smaller than at pre-industrial and polar temperatures were higher, you might expect that global mean sea level would have peaked higher in the Holocene than at pre-industrial. And we have to sort of go at it this way. I'm going to argue, in order to get Antarctic rates of change, which is what maybe we really want to think about for future projections. So the state of the field up until now has been these three curves. So global mean sea level is on the y-axis, and time is still going right to left on the x-axis. So all of these three curves from about a decade ago show sea level rising to the present. And the most kind of influential of these, arguably, is Lambeck et al. 2014. Lambeck and colleagues used about 1,100 sea level data from sedimentary samples and corals, mostly in Southeast Asia and Australia, and it's an excellent piece of work. It has been the state of the field for the last decade, but as we are starting to get at this question, how high did global mean sea level get in the Holocene, we wanted to ask, what's the most up-to-date algorithm that we can use to get at this question, and how much data can we marshal to present the most up-to-date picture we can for Holocene sea level? So it turns out on the data side, the last decade has seen a concerted effort by the Holocene sea level community to compile and standardize the world's sea level data. And that's resulted in about 6,000 relative sea level data from places like salt marshes, mangrove swamps, coral microatolls, what we were talking about before. About 6,000 of those data that we're looking at here in orange. I added about 4,000 additional published data to that database to get us to about 10,000 relative sea level data, mostly for the last 12,000 years, some a little bit younger. So we've got 10 times more data than Lambeck and colleagues did. On the algorithm side, we also wanted to take advantage of computational resources that are now available and build a new algorithm. So this is a bit busy, but we're going to step through it. So we started from reconstructions of what ice may have been doing over the last 80,000 years, and this is putting together as many published versions of Laurentide histories, Eurasian ice sheet histories, Greenland histories, and focusing on Antarctic ice sheet simulations, partly because more of them are available, but mostly because Antarctica is the big player in Holocene sea level. But then also mountain glaciers. So we looked through the literature and said, has anyone reconstructed mountain glacier volume in the Holocene? Because we would have just used that. Unfortunately, they hadn't. So we had to come up with a way to reconstruct Holocene mountain glacier volume. Okay, mountain glaciers. So this is a figure showing where mountain glaciers are on Earth now. There's about 200,000 of them. These are glaciers not attached to the major ice sheets. So you see a bunch of them around Greenland. All those glaciers are not physically attached to the ice sheet. And it's only been in the last really decade when, thanks to remote sensing, what's called the Randolph Glacial Index or inventory, we've been able to get the outlines of all 200,000 of these mountain glaciers and then estimate their volume. So from that, some intrepid researchers ran the clock back 100 years to 1900 to get mountain glacier volume in 1900, which is not quite pre-industrial, but it's the best that we can get. So what we did was to take mountain glacier volume at 1900 and say, we can't actually estimate mountain glacier volume through time. We can't do that modeling, but we do have gridded temperature estimates through time through a combination of temperature data and models. This is kind of a product that a bunch of groups have put out. Temperature everywhere on Earth's surface for the last 24,000 years. So then the key assumption is to say mountain glaciers are small enough bodies of ice that it's not a terrible assumption to say that over a 100 to 200 year time step, mountain glacier volume is in equilibrium with temperature. So we don't have volume, but we have temperature. So let's scale the 1900 mountain glacier volume up and down following local temperature. And this relationship that Marzian and colleagues developed between temperature and glacier volume. Now, you'll notice they mostly cared about positive temperature because they care about how fast will the mountain glacier melt in the future, which is great. We needed to go colder as well. So barring any better information, for places where we didn't have data, we used a linear prior to derive a rough mountain glacier temperature scaling relationship. So with that and with gridded Holocene temperature products, we were able to create a first estimate of Holocene mountain glacier volume. And the takeaway is, looking at glacier volume in meters of global mean sea level equivalent, mountain glaciers probably in the Holocene didn't contribute more than, say, 15 centimeters to sea level. But to put that in context, that's the same order of magnitude as the sea level rise, global average sea level rise from 1900 to now. So it's not a trivial amount of sea level. Okay, so that gets us an ice sheet ensemble with 26,000 different ice sheets for the last 80,000 years. We then needed to include one more piece, which is thermosteric sea level. So what is thermosteric sea level? And here again, there was no estimate of Holocene thermosteric sea level, so we had to make one. So for those who aren't familiar, thermosteric sea level, cold water shrinks, warm water expands. This right now is accounting for about a third of sea level rise. Is the oceans expanding as they absorb heat from the atmosphere? So in the modern environment, not a trivial contributor, quite a significant contributor to sea level. So what we did was take a very cool proxy from Shackleton et al., Sarah Shackleton's group. And this proxy is from Antarctic ice cores. It's ratios of xenon, krypton, and nitrogen, which it turns out is a good proxy for mean ocean temperature. Like mind-boggling that we can get mean ocean temperature from Antarctic ice cores, but there it is. So they have mean ocean temperature through the Holocene, and we used an equation of state to convert that to ocean thermal expansion and contraction. And the takeaway is that in the Holocene, mean thermosteric sea level probably not more than about 25 centimeters, but that's a non-trivial contributor. Okay. So combine the ice sheet ensemble with glacial isostatic adjustment modeling, which we talked about earlier, and you get an ensemble of about 2.3 million GIA models. Compare those to the sea level data that I showed you, and you get data model misfits. Nothing hidden here. We're comparing GIA models to data. That gives us a fitness score for each ice model. The fitness score for each ice model converts to a global mean sea level, weighted global mean sea level curve, and that gets us to an estimate of global mean sea level. So now some results. We estimate that global mean sea level, it is 79% likely, exceeded 1850 sea level sometime in the last 7,500 years, and that it reached about 30 centimeters higher than present with significant error bars around 3,000 years ago. And so that's the black curve that we're looking at here with the blue envelope, and compared to these other curves. So we're consistent with previous results, but quite a bit higher than Lambeck and colleagues. But what's interesting is that if you dig into Lambeck et al. 2014, into their supplement, you find that they basically, the results of their modeling was a 50-50 coin toss between the curve that you see and that red curve. And on very little evidence, they chose the lower version and said there's not enough independent observational evidence to constrain what was going on really over the past 7,000 years. So you could say the right answer was there all along, they just chose the wrong one. But I mean, again, our uncertainty bars are big enough that all of these fit into the final result. But I told you that we were going to connect this to Antarctic mass loss rates and compare past to future, so let's do that. So here's those same scores that we used to create global mean sea level. We could also apply to the Antarctic Ice Sheet simulations that we used in this study in order to get Antarctic rates of Antarctic change. And so here we're looking at that for the Holocene and then comparing to the future. And just like eyeballing it, you kind of see that over the last 6,000 years or so, Antarctica is not doing a ton in these simulations, but then start to look more at the 8,000 years ago, and you get faster rates of Antarctic change. We'll come back to that in the second part of this talk. One other way of looking at these data is to say, when will Antarctica be losing mass faster than it did in the past? Or let's compare past to future and say, how likely is it that Antarctica will be losing mass faster by 2100 than it did in the past? For the last 3,000 years, 4,000, 5, 6, 7, 8, 9, 10. So the way to interpret this is to say it's very likely that future change will be faster than the last 3,000 years, but very unlikely that future change, except for this like very high emissions scenario, it's very unlikely that the future over the next 100 years or so will be faster than the last 10,000. Okay, part 2. How does Antarctica respond to abrupt climate forcings? Okay, so the last abrupt climate event, the most recent abrupt shock to the Earth system happened about 8.2 thousand years ago. So now we're looking at North America, and we have what's left of the Laurentide ice sheet sitting on the Hudson Bay, and there's a proglacial lake, Agassiz Ojibwe, that it's blocking. So this big ice-dammed lake, and around 8.2 thousand years ago, that water floods out into the North Atlantic. Whoop. Very fast. It ripped up a whole bunch of sediment. Wouldn't want to have been standing there. And so one question that you might have thinking about this is, like, what happens to the ocean circulation system when you dump fresh water into the North Atlantic, and how does that refer down to Antarctica? So I'm going to walk through a set of premises for how this might have proceeded. Okay, so premise 1. When the 8.2 Ka event slowed overturning circulation by dumping a bunch of fresh water into this global conveyor system, the Southern Ocean warmed. So it turns out that this is a whole subfield of what ocean modelers call ocean hosing experiments. So what we're looking at is how air temperature, how ocean temperature responds when you put a bunch of fresh water into the North Atlantic, about as much as we think got dumped in there 8,000 years ago. And the answer is the northern hemisphere cools, the southern hemisphere warms. Here's 3 other studies on, with different color maps, but the same color bars. And thankfully, they come up with similar results. Cold in the northern hemisphere, warm in the southern hemisphere. Okay, premise number 2. As the Southern Ocean warmed, circumpolar deep water penetrated the Antarctic continental shelf. So this is happening right now. And the mechanism, schematically, is like in the control case, circumpolar deep water comes up almost onto the Antarctic shelf, but not quite, and converts into Antarctic bottom water. This is modulated by easterly and westerly winds. But as easterly and westerly winds change speeds, that change in wind draws circumpolar deep water up onto the continental shelf, which changes basal melt conditions and melts the edges of the Antarctic ice sheet from below. Premise number 3, when circumpolar deep water penetrated the shelf, the Antarctic ice sheet thinned. And so to support this claim, we're going to just flash up a bunch of papers because the literature on this is pretty extensive. Folks thinking that West Antarctic ice sheet retreat may have been driven by Holocene warm water incursions. Ocean is the main driver of Antarctic ice sheet retreat during the Holocene. You could just keep kind of flashing these papers because there's a lot of folks arguing this. Okay, so then thinking about how does Antarctica respond to abrupt climate forcings, maybe the question that we need to be asking is, how did Antarctica respond to the 8.2 Ka event? And so the methods that we're going to marshal to get at this question are 3 independent sources of evidence. We're going to use the parallel ice sheet model, which is a certain numerical model of ice sheet evolution, the ensemble that we used for part 1. We're going to use what are called cosmogenic nuclide exposure age thinning profiles. I'll explain what that is. And we're going to use marine sedimentary data to get at this question of Antarctic change since last glacial maximum. Okay, so first, ice sheet modeling. So I showed you this graphic, and we said, there's something interesting happening around 8,000 years ago. And it has a red circle around it. Unfortunately, the color map on this desaturated, but you can see the mean and the median there. And what's important to take away from this rate of contribution to global mean sea level for Antarctica over the past 20,000 years are these spikes. There's a bunch of spikes. And so look at that and say, why is Antarctic thinning spiking over the Holocene and deglaciation? Because the model, the PISM model that we're using, has only certain boundary conditions. So whenever you're running a model, you're trying to understand its behavior, it's important that you think about how you're forcing the model. Like what's pushing the model in various directions. And what's pushing this model, on the sea level side, we have global mean sea level change. So there's some nonlinear rates of sea level rise affecting this ice model. We then have air temperature from an Antarctic ice core. So air temperature is modulating ice behavior. And then, crucially, this model doesn't have independent ocean temperature. It only has the same air temperature record that's smoothed and with a lag. So whatever is causing these spikes in Antarctic thinning, it's coming from either air temperature or sea level rise in this model. Okay. So in the original version of these slides, that's red, and 8.2 is right there. And the takeaway is the 8.2 event itself doesn't really overlap with any single one of these spikes. But, so what I started to think was, okay, what what nonlinear phenomena in the Earth's system might be causing Antarctica to change rapidly in this model? So one way that fairly continuous insulations, like sunlight hitting the northern hemisphere, fairly continuous sets of forcings can lead ice sheets to have nonlinear responses, is what's called ice sheet saddle collapse. So imagine you have a saddle, you have ice that's high on two sides, and then this divot in the center. Well, that divot is lower in elevation, so it's warmer, which means that it melts faster. So as an ice sheet melts, saddles tend to collapse and ice sheets split from single dome to double dome with a boundary between them. So ice sheets, saddle collapse is one way that you can suddenly cause fast rates of change. And so the next step was to say, let's look at what the northern hemisphere is doing in the Holocene. So here, these two lines, it turns out, line up quite well with radiocarbon-based reconstructions of the Laurentide ice sheet, a North American ice sheet. As it collapsed, it had saddle collapses of the Cordilleran ice sheet. And then the Inuitian ice sheet, another sector of the Laurentide ice sheet, has sectoral collapses there. And then finally, the nucleus of the Laurentide ice sheet has collapse events that line up surprisingly well with Laurentide ice sheet with these sectors collapsing. So it seems like maybe there's a story about northern hemisphere ice sheet saddle collapse referring down to the southern hemisphere to drive Antarctic change. And if you split these results up into various sectors, so the Ross Sea, Weddell Sea, East Antarctic margin, different sectors are melting at different times, but I've plotted these lines onto these sectors, and the different sectors are aligning with these saddle collapse events. Okay, so we have a story of maybe Laurentide ice sheet saddle collapses linked to Antarctic deglaciation. Thinking about that with pictures. So this, to our best knowledge, is how much spatially ice melts from the Laurentide ice sheet between 16 and 13,500, and based off of these sectoral reconstructions, and in this case, a bunch of other research suggesting that this period had this saddle collapse hypothesis that those sectors of Antarctica are responding. Cordilleran ice sheet splits apart 13 to 11. Inuitian ice sheet saddle collapses, and then finally we have the Laurentide splitting apart. So what causes this teleconnection is the question, because I showed you images of this ocean atmosphere modulated teleconnections, but we also know that because of the fingerprint of ice sheets, when you melt northern hemisphere ice sheets, Antarctica responds particularly much. So there's a combination of atmospheric effects and sea level forcing possibly being the explanation. But then what about ocean forcing? Because we also talked about circumpolar deep water stepping up onto the continental shelf. So then thinking about how does Antarctica respond to abrupt climate forcings, maybe one of the questions that we need to be asking is how did Antarctica respond to ocean forcing since last glacial maximum? So that brings us to the second part of this, three sources of evidence: cosmogenic nuclide exposure ages. So what are cosmogenic nuclides and how do they help us tell this story? Earth is being bombarded at all times by energetic particles from the sun and other stars. Those particles interact with our atmosphere, and when the products of that interaction hit exposed ground, the chemical reactions that ensue produce elements like beryllium-10 that we can measure in rocks. Now, if bedrock is covered by enough water, by enough ice, that bombardment doesn't reach the bedrock. So if we have an ice sheet covering mountains, mountains are not getting bombarded, and there's no beryllium production. But as the ice sheet thins, progressively, more and more rocks are exposed on the mountain. So in this schematic version of things, we have then a transect of elevation versus exposure age, telling us that the oldest part, the highest rocks on the mountain were exposed first. So we can use this to reconstruct ice sheet change through time. That's not a very high resolution image. Sorry about that. What we're going to look at is, we're going to zoom in to Antarctica to see what this sort of data looks like. So Antarctica, we're going to zoom into West Antarctica. West Antarctica, we're going to zoom in to an area called the Pierrot Hills. So now we're looking at the Pierrot Hills. We're going to zoom further in to stand on the ice. So now we're looking at Mount Axtell, Mount Tidd. And we're going to then zoom in even further and say, let's hike up the mountain and notice that all these boulders are sitting on the mountain. I want to flag that I did not do any of this field work. I do field work, but not this kind. And so these folks are heroes who sacrificed their lives and perhaps their relationships to collect these data. I hope not. But the community of folks doing this work has created a beautiful database called the ICE-D, Informal Cosmogenic Nuclide Exposure Age database of these data, which we're going to use in this study. Okay, so this sort of fieldwork produces age versus ice, elevation above present day ice. And so my intervention on this database is to fit those data with a smooth statistical model, penalized spline regression. Colors are not showing up, and that's fine. The point is to say there are some locations like this where the data are not that numerous and it's easy to fit them. There are other places where you have to be a little bit nuanced in fitting these different data. But what we did was to take data from around Antarctica, that's these different rainbow-colored circles, size of circles, number of data, and then estimate thinning rates for these different parts of Antarctica through time. And that's what we're looking at here. So here we have percentage of sites thinning, well, the color bar goes from hot, fast rates of thinning down here to slow rates up here. And the point is that thinning is not continuous through the Holocene and through the deglaciation. There are times when thinning hits its maximum. The 8.2 Ka event is about right there. So it lines up quite nicely with increased rates of thinning. Ha-ha! Ha-ha! And so now I've overlaid these different sectoral saddle collapse events. And what you see is that there is quite some correspondence with northern hemisphere change and Antarctic thinning, but also there's a bunch of other things happening. So the Laurentide is done by 7,000 years ago. There's still quite a bit of Antarctic thinning after that. So air temperature, sea level can't be the whole story. Might be oceans doing the work of this continued thinning. And if we switch now to a sector by sector, interestingly, the places the sectors where there's a lot of thinning late in the Holocene also correspond to areas with marine-based ice sheets. So the Ross Sea, the Weddell Sea, Amundsen Sea, these are places where there's a lot of the ice sheet interacting with the ocean. And we might expect that the ocean would be having an effect on the ice sheet. Okay, so finally our last piece of evidence, marine sedimentary data. And I'm just going to show a few examples of these sorts of data. So for instance, here's Antarctic Peninsula. This is from Leroy and John Anderson from Rice, 2007. So they took these sediment cores from Antarctic Peninsula and traced this line through the data that they think are most reliable. And what they highlighted was meltwater pulse 1A, meltwater pulse 1B. These are two time periods with very rapid sea level rise. So they at least think that the Antarctic Peninsula is retreating in time with these meltwater pulse events that actually correspond to saddle collapses from the northern hemisphere. One other case study in the Amundsen Sea. So now we're going to look at data along this profile. And so here, similarly, we have a best fitting line through these data. Time is going from 20,000 to 0. And if you overlay these two, Amundsen Sea and Antarctic Peninsula, on our thinning profiles, I think you could argue that there's rapid thinning kind of aligning with these time periods of northern hemisphere rapid ice sheet change. And this is then that same figure, but with the model thinning. So I want to leave you with this story of the northern hemisphere talking to the southern hemisphere over the last 20,000 years, which I think is important as we think about how is Greenland going to melt over the next 100 plus years. Greenland has about one ice saddle left to collapse, and what effect will that have on the southern hemisphere? So, some takeaways from this section of the talk. Atmospheric and sea level teleconnections, we're going to argue, could link Laurentide ice saddle collapses to Antarctic mass loss. However, ocean forcing, we think, explains or could explain some of the remaining Antarctic change, including during the 8.2 Ka event. And to reproduce Antarctic deglaciation, it may be that ice models will need to think about including ocean forcing from marine proxies rather than or in replacing scaled air temperature, which will require more investment in getting these marine proxies for ocean temperature up to a level where we can use them in a meaningful way. So with that, I want to thank the collaborators on this project. Science is a team sport. None of this would have happened without these brilliant people. So thank you so much, and I'll take questions.
Questions? Wait, we're going to stop the students. Do you guys have questions? Don't be shy. Questions? Exactly, Swan. No?
Yeah, I think especially like all of those constantly which I relative targets of this stuff.
Thank you.
Yeah, I'm doing this by the part of the question because I'm doing so on the ocean plus for me, I still is the same instead of horizontal to show clearly from the number has been ice sheets instead of outside spikes. So the spikes means has changed. This will cause the rapid signal ice sheet. So how you just connect to the ocean forces? So I really miss this.
Yeah, so let's call this a hypothesis. So the observations that we have are we have an ice sheet model that's forced by sea level and air temperature, but not independent information from the oceans. And the combination of those forcings is leading to thinning rates that align with northern hemisphere ice saddle collapse. So causation in paleoclimate is a really dangerous game. So I think in order to test that causally, you would need to have a full, a global ice model where you could turn knobs, ice sheet coupled to glacial isostatic adjustment model, solid earth coupled to ocean model, where you could turn knobs and see how those signals referred through ocean, sea level, and atmosphere. But what we're arguing here is that because is that the difference between the cosmogenic nuclide thinning profiles and this ice sheet, this model only forced by air temperature and sea level, the difference is that thinning profiles have a chance to be recording information from the oceans as well as air and sea level. And so, kind of by subtraction, given that major northern hemisphere ice sheet change had finished by 6,500, 7,000 years ago, but the Antarctica keeps changing. So there's rapid pulses in thinning even after ice saddles are gone. We need another explanation for why that's happening. And one possible explanation for that is that it's ocean forcing. Yeah.
Yes.
I know you said you were talking for a minute about Antarctica and how the north talks to the south
Yeah.
ocean, but does your research go into like what does the south say to the north, like in like what Antarctic ice is saying to the Greenland ocean?
I love that question. From first principles, we might expect that Antarctica talking to Greenland, Antarctica could have talked to Greenland through the oceans. I mean, this is personifying ice sheets, so flagging that. There could have been signals referring from one to the other through the oceans more successfully earlier in the deglaciation when more of the Greenland ice sheet was connected to the ocean. Right now, those connections are more through smaller outlet glaciers. So Greenland ice sheet, I think in the Holocene, ice sheet modelers would probably agree that surface mass balance matters, and like the ice sheet's responding to local temperature. It's still possible for Antarctica to be interacting with Greenland through teleconnections, but I think the oceanic link is not quite as strong. Yeah, but I mean, the Laurentide and the Eurasian did both have significant marine-based sectors, so then you would need to think about how could thinking beyond just the sea level forcing, which would be real, like the fingerprint of Antarctic melt would relate to the northern hemisphere, but are there more ways that it could go from south to north? That's definitely a question that we need to be thinking about as we have two ice sheets that are melting fast at the same time. Like, do they cancel each other out? Do they add on top of each other? That's important.
Great talk, thank you.
Yeah. Go ahead.
Yeah, just maybe think of another question, Roger, that kind of links the second part of your talk, the first part of your talk, which is like if the ice sheet is responding to these saddle collapse events, is it responding to the total amount of sea level change over that saddle collapse, or is it actually responding to the rate? And if it responded so sensitively to the rate during the deglaciation, do you expect that, I mean, you just said in the first part that like the sea level may rise faster in the next 100 years than it has during the Holocene. Do we start to approach the rates at which you know that Antarctica responded to saddle collapse events during the deglaciation? Does that make sense?
It does, and it's an excellent question. The last time, next 100 years, we probably won't quite hit the 8,000 year range of Antarctic rates of change. But I think what we need to hone in on is to say which of the three mechanisms, sea level, air, and ocean, which of those is driving the change. Because if it's seeable, then what we care about is like the volume of mass, the volume of ice that's melting. But if it's the fresh water dumping into the North Atlantic that's slowing ocean circulation, then maybe we don't need a saddle collapse if Greenland is melting a lot. So I think it's nuanced, and I think this is kind of a call to arms for folks who have the capacity to model ice sheets, responding to the solid Earth, and interacting with the oceans, to tease out those mechanisms. Is it ocean circulation? Is it the solid Earth GIA kind of teleconnection? Yeah.
So it seems like there is an oceanographic difference that could be maybe leveraged. So Cordilleran ice sheet puts fresh water in a very different place than Laurentide ice sheet puts fresh water, or Greenland puts fresh water. So the early part of your thinning signal has a very different oceanographic forcing than the late part of your thinning signal. But it doesn't look like you see that in Antarctica. Or could you say that the greater thinning is because there's a more direct oceanographic connection?
Yeah, excellent question. I think to answer that, I'll be walking out on the tightrope, but I'll do it for you. So I think one way that you could get at this would be to say, yes, Cordilleran ice sheet. If the Cordilleran ice sheet's the brown, so we can test this. Would we expect that Cordilleran ice sheet melting would refer down to the Weddell Sea specifically? I don't know. Like from first principles, it's not obvious to me why that would be the case. But it is clear that there is melting in the Weddell Sea at that time, or at least there's thinning, which is not quite the same as melting, but there's something happening there. So we have to explain the observations, and these are all correlational. But I think it's targets for modelers to shoot at.
Dave?
I have a question about precipitation, which somehow must get folded into air temperature, but I'm wondering if that, what sort of accuracy that can be done